Welcome to the Introduction to Hyper-Optimization online training. My name is Marlon Price. This training is part of a series of training courses highlighting the FPGA design process when targeting Intel FPGAs made with the Intel HyperFlex architecture. By the end of this training, you will understand what is meant by hyper-optimization, the reasons behind why you may or may not need to do it, and how it relates to loop structures and their impact on your FPGA's design performance. You will also understand the steps needed to begin the process of performing hyper-optimization. To do this, we will start with a look at hyper-optimization basics. Then we will see how fast-forward analysis can be used to locate places in your design where a hyper-optimization solution might be necessary. So we begin with hyper-optimization basics. Hyper-optimization is the process of evaluating design behavior and making changes to the RTL so as to increase the benefits of hyper-retiming and hyper-pipelining. Essentially, you use hyper-optimization when you want to achieve clock speeds faster than what is possible with just hyper-retiming and hyper-pipelining alone, or making changes beyond simply removing retiming restrictions and adding more pipeline stages. Most of hyper-optimization involves loop management, since loops serve as barriers to the benefits of retiming. So any manipulation of loops to reduce or eliminate their effects to retiming falls under the heading of hyper-optimization. But hyper-optimization can also involve explicitly placing registers and locations beyond just I/O and clock boundaries, or in other words, internal locations not targeted by the hyper-pipelining methodologies we discussed in earlier courses like this one. Here we see an example of hyper-optimization at work. This circuit includes a series of 4 combinational logic ALMs within a long single register feedback loop. As shown, this loop could be a limit to the design's performance, as there is a potential for the timing delay around the loop to be a critical path to this design. Now we have used an advanced optimization technique to restructure the design to produce a functionally equivalent circuit that includes a much smaller loop. Thus, the impact of the loop is minimized since it's down to a single ALM and a single register, and all the loop functionality is now in the forward path leading up to the loop. Once in the forward path, this logic can take advantage of the HyperFlex architecture and be pipelined and thus retimed. Loops are barriers to hyper-retiming because the loop functionality depends on loop data arriving after a certain number of clock cycles. In this example, there is a 1 cycle delay around the loop before the loop value is combined with a new value. Thus, changing the cycle delay around the loop by adding or removing registers to the loop path would change the functionality. So it is an illegal move for the hyper-retimer. Though the hyper-retimer cannot change the number of registers in the loop path, it is free to retime registers clockwise or counterclockwise around the loop. This it may do to improve the loop's performance. If a register is retimed completely around the loop in one direction, it makes it appear that the output registers to the loop jump over to the input side. If the register is retimed the other direction completely around the loop, it makes it appear that the input registers to the loop jump over to the output side. The software is aware of this and will use this strategy to retime registers over or through loops to the other side if it results in a performance gain. Of course, the hyper-retimer can choose intermediate locations within the loop for the registers if this increases the performance of the loop. In this single register loop example, we're going to retime the register counterclockwise. As the register moves past an output junction, a duplicate register must retime into the output path, since that junction is a retiming dependency node. So retiming the register halfway around the loop, you end up with the circuit on the right. If we continue retiming the register counterclockwise, the register passes an input junction. In this case, An equivalent register must enter the loop from the input path, again because this input junction is to a retiming dependency node. So retiming the register the rest of the way around the loop, we end up with the circuit on the right. So if we retime the register in the loop for an entire revolution, it will appear as if the input register has hopped over the loop to the output side. Thus, both of these circuits are functionally equivalent and legal from a retiming perspective. If we rotate the register clockwise, then the output register would jump from the output side over to the input side. But we cannot change the number of registers within the loop. Unlike any of the solutions from the previous slides, this action would change the functionality and is an illegal move for the hyper-retimer. In this example, the circuit expects the feedback value to appear one cycle later. Adding a second register makes the feedback value appear 2 cycles later, again changing the circuit behavior and the output results. Whether this breaks the circuit's actual functionality is dependent on what the circuit is actually doing, but the hyper-retimer cannot legally assume it will not. If a loop contains a single register, then no matter where the register is placed within the loop really can't get any faster. If the loop contains more than one register, then the hyper-retimer will retime the registers as needed for best performance, spreading them out as much as it can to average the delay between them. As it does so, and the registers pass loop input or output junction points, duplicate registers will again be pulled into or pushed out of the loop path. But again, the total number of registers in the loop is still fixed. This works the same for a single bit loop path or a multi-bit or bus loop path. So why are loops suddenly now an issue? The problem with loops isn't really new. There's plenty of literature that shows that people have been aware of the potential problem with loops for a while. But up until now, other types of design paths were primarily responsible for FPGA performance limitations. In other words, FPGA designs were not going fast enough to consistently expose loops as the problem. With the HyperFlex architecture, this changes. The fabric can now support much higher clock speeds to where loops can become a significant limiting factor. Here's some notes on hyperoptimization. Hyperoptimization is work. Hyperoptimization is only necessary if you desire clock rates faster than what is possible with hyper-retiming and hyper-pipelining alone. If you're already happy with the clock speeds of your design from the first two methods, then there really isn't much reason to go down the hyperoptimization path. Also, not all of these performance limitations are the result of bad code. It's just that certain design structures have natural performance limitations to them, and the speeds of the HyperFlex architecture exposes them. Hyperoptimization will almost always require changes to your RTL. Again, if you want to go beyond the limits of your current design, then you have to be prepared to modify it. How much performance gain you get is dependent on what the design currently looks like and how much time you want to spend. Some designs will require a lot more time and effort and a lot more modifications to go through the hyperoptimization process than others. Then finally, in general, if your design has already been optimized to achieve 300 megahertz or more in an older FPGA family without the HyperFlex architecture, then you may have to explore hyperoptimization to see a more significant gain. This is because most of the simpler optimizations to reach that 300 megahertz or more, like adding additional pipeline stages, will probably have been done already to the design. Next, always make sure you resimulate the design after any hyperoptimization. You must verify that your design functionality has not been changed. If you make optimizations for one device with the HyperFlex architecture, those optimizations will translate to other devices with the HyperFlex architecture, so you can feel safe in the knowledge that your work will translate. And finally, Most hyperoptimization techniques are simply faster structures from a timing perspective, so they will produce a performance improvement even when used on older device families without the HyperFlex architecture. The HyperFlex architecture and the addition of the hyper registers just serves to increase the effectiveness of the techniques. If you're going to do hyperoptimization on your design, here are some things to think about. When are the signals or values you need for a computation actually available? This could impact when you perform the computation, potentially doing it earlier or spreading it out over multiple clock cycles. When do you need a particular computation result? If the result is actually needed later than when it is produced, you have the potential to do some sort of pre-computation. What are the signals that are causing the timing issue, and when are those signals needed to produce the result? Again, instead of trying to do a computation or evaluation in the least number of cycles necessary, you might be able to move the use of the signals causing a timing issue across more clock cycles. And finally, how much flexibility do you even have? That will determine what kinds of hyperoptimization might be candidates for you. In this next section, like we did with hyper-retiming and hyper-pipelining, let's take a look at how we can use fast-forward analysis to perform hyperoptimization. Just like with hyper-retiming and hyper-pipelining, fast-forward analysis will perform some hyperoptimization and list those recommendations in its output report. They will appear as hyperoptimization step numbers. Just locate the clock performance you're trying to achieve, go to that fast-forward step number, and implement the design changes you see there. In this case, there is no need to know or do anything about the detailed critical chain analysis. Currently, Fast-Forward Compile does one type of hyperoptimization design modification, which is DSP and RAM block analysis. Other types of analysis may be added in future versions of the Quartus software. During fast-forward analysis, the block registers of the RAMs and DSPs can be turned on if they have not been enabled by your RTL. This will show you the performance possible if this modification was made. Knowing this, you can confidently return to your RTL and modify the code to enable these registers to achieve the fast-forward analysis predicted clock speeds. Please see the Quartus documentation for examples of how to write your RTL to ensure these registers are used. Here is a screen capture of a fast-forward report showing hyperoptimization steps. Here we can see that step number 1 requires fully registering a DSP block to increase the performance by just over 50 MHz. After that, all of the subsequent fast-forward steps show additional modifications being performed, but they are still labeled as hyperoptimization as they are all dependent on step number 1 taking place. In the lower screen capture, we see an example recommendations for critical chain tab for a base performance step. Here we can see the report is indicating that there are DSP blocks with registers not enabled and recommending the designer enable them for the performance improvement. Not all fast-forward hyperoptimization modifications are possible for a designer to implement, so to return them as a solution would be useless to you. So you have the ability to reject certain recommendations. In this case, you can reject the enabling of RAM and DSP block registers. This forces fast-forward to return a solution that you can or intend to implement. There are two QSF assignments that you use to control RAM and DSP block register enabling. They are fast-forward compile fully register DSP blocks and fast-forward compile fully register RAM blocks. Just set the assignment from its default on setting to off to prevent fully registering the blocks, if they were not enabled by your RTL. These QSF constraints can be applied globally to the entire design, or every instance of a certain block, or locally to a specific instance of a particular block. The other way to use fast-forward for hyperoptimization is if you're trying to reach the maximum performance for your design, or a performance value beyond the final fast-forward prediction. In this case, you will want to go to the fast-forward report for your clock domain and go to the last line, the fast-forward limit step. You can choose to bypass the other steps in advance, or you can do the other steps first and then go to the fast-forward limit. The fast-forward limit is pointing you to the real performance limitation of your design. This is because for all the other fast-forward steps, the analysis was able to modify the design and thus get past those limitations. For the fast-forward limit, fast-forward has reached a critical chain that it is not able to modify its way past. So now it is up to you as a designer to figure out how to get past this limitation. To increase the effectiveness of your hyper-optimization using the fast-forward limit, you can run multiple seeds in parallel. We recommend around 5, but this number is dependent on the number and size of the computing resources to which you have access. But running multiple parallel seeds can save you significant time spent in performing hyper-optimization. Since each fast-forward analysis produces a single fast-forward limit, it may take multiple design iterations for you to locate each of the loops that need to be fixed. So by running multiple compiles, you can gain a better picture of how to proceed with your optimizations and potentially reduce the overall time spent optimizing. Of course, running multiple compiles in parallel requires that you have the computing resources necessary to do this, such as an available server farm. So how does this work? Let's say after running 5 seeds, a loop shows up as a fast-forward limit in only one of them. This could be an indication that the loop fast-forward limit is only a result of a particularly poor placement. Thus, you can choose to ignore the loop at this point. Of course, if you decide to spend time optimizing a loop, it may help things further, but again, that work may not be necessary. Now let's say you have a loop that shows up as the fast-forward limit in multiple seeds. Well, then this would be a good indication that this loop is indeed critical and worth any time you spend optimizing it. Finally, let's say you have multiple loops that show up as the fast-forward limit in different seeds. For example, one loop may appear in 3 different seeds and the other in 2. This might indicate that you have multiple critical loops in your design. Now you can spend time addressing them both at once, eliminating the need to do iterative compiles to learn the very same information. This process is even more useful if you have an idea of the seed variation of your design. This will help you eliminate outlier solutions or the performance of really good seeds or really bad seeds, in other words, solutions that may be challenging for you to repeat. One thing to keep in mind is that loops are a very common design structure. This means that not all of them are going to cause you critical performance limitations. So there is no reason to systematically try to go through your design in an attempt to optimize all of them. Some loops may be very tricky to optimize depending on their function and what they're connected to. Some may require pretty drastic or complex restructuring. So this is how fast-forward analysis can help. It can point you to the loops that are truly limiting your performance so you can focus your efforts only on the loops that need modification. So to identify the performance limiting loop, you want to go to your fast-forward compile report and select the fast-forward limit. There you want to look down at the Critical Chain Details tab. This critical chain should be pointing you to the performance limiting loop in question. For many designers who have an intimate knowledge of the design, just seeing the node names in the critical chain details will be enough for them to know exactly where the offending loop is in their design. If that's the case for you, then that's great. You know exactly where to go to begin looking in your options for optimization. If you need some assistance in locating the loop, then here are 3 methods you can use: drawing a simple block diagram, using the fast-forward viewer, and using the RTL viewer. The first method is to draw a simple block diagram. Now this should be pretty simple. The goal of this diagram is not to draw an exact replica of the critical chain. It is only to get enough of the critical chain right so you can figure out where the loop is. And then from there you can determine the best solution for it. So draw enough of the chain so you can correlate the picture to your understanding of the design. The second method is to cross-probe to the built-in fast-forward viewer in the Quartus software. Just right-click on any line in the critical chain report and select Locate in Fast Forward Viewer. This will open up the Fast Forward Viewer with a graphical display of the critical chain, similar to cross-probing from the timing analyzer to the technology map viewer. In this view, you can identify registers in the chains by means of their assigned ID numbers. You can expand or collapse the logic clouds as needed to gain further understanding. But again, the goal is just to find the loop. So you just want to understand enough of the fast forward viewer display so that you can correlate what you're seeing to your knowledge of the actual design. Keep in mind when using the fast forward viewer that the design paths that you are viewing have gone through synthesis, fitting, and retiming, so sometimes the paths look nothing like the code you actually written. Logic could have been compressed or combined in various ways, or registers could be placed in locations you do not expect. This can make this view very difficult to interpret. So the last method for locating the loop is to cross-probe from the Hyper-Retiming report to the RTL viewer. The RTL viewer's display will be much closer to the original RTL, so it may be easier to understand the circuit. The trick here is finding the processed node names from the critical chain back in the RTL. For that, we recommend starting on a register in the critical chain. Right-click and in the Locate Node submenu, select Locate in RTL Viewer. This will open the RTL Viewer with the register highlighted. Then right-click on the register and from the Filter submenu, select Sources and Destinations. This will then show you the paths leading to and from that register. Hopefully again, this will be enough for the loop path to start presenting itself to you. If not, you can try filtering or extending the path even further. Again, the goal is to locate the loop, so choose whichever method works best for you so that you can then begin to work on your solutions. Please note that loop critical chains can become very complicated with loops within loops and zigzags. This is all determined by the complexity of the logic functions in the loop. This can make deciphering and understanding the loop very challenging, depending again on your knowledge of the design. In general, the more segments in your loop critical chain, the more complicated the loop will be, and the more work it might take to solve it. But using the tools we've seen here, you can locate the loop and begin investigating those potential solutions. This concludes our Introduction to Hyper-Optimization online training. In this online course, you learned that hyper-optimization is the last stage of optimizing a design for the HyperFlex architecture, and that it involves analyzing and potentially restructuring the design to achieve performance gains beyond what is possible with just hyper-retiming and hyper-pipelining alone. You also learned that most of hyper-optimization involves reducing the impact of loops on retiming. To aid in the process of implementing a hyper-optimization solution, you learn to use Fast Forward Compile as it can point you directly to the paths in your design that require this improvement. If you would like to continue in your learning on the HyperFlex architecture design flow, Intel recommends the follow-up hyper-optimization techniques training shown on this slide. Intel FPGA provides many self-help resources when you need design assistance. For example, there are web pages called landing pages dedicated to specific FPGA technology like transceivers, DSP, OpenCL, and high-speed gigabit interfaces. There is a community forum, and there are hundreds of training courses available just like this one. One last thing, when you register for this training, a link was sent to you in your confirmation email that links to a short online survey. Please complete the survey to let us know what you think of this training and if you can think of ways in which it can be improved. This concludes this online training. Again, my name is Marlon Price. Thank you for your time.